Hey guys, in this video I just want to take a look at finding the domain of a function from just looking at the rule for the function and not looking at the graph, which is a little bit different thing. So remember, when we look for domain, there are two things that I want you to look for. We're going to exclude any x values that satisfy one of two conditions. One is that we divide by 0. We never want to do this. It's undefined. So division by 0 would be an excluded thing. We wouldn't want to do it. And we don't want to take the root, I'm going to write even indexed root, because if I wasn't, I wouldn't be doing my due diligence. But even indexed root, that's like square root, fourth root, sixth root. You can't take the even indexed root of a negative value. And so that being said, what I'm going to show you again is just kind of what you would do in these situations to determine, say, the domain of functions from their rule, just by looking for these two caution signs. So when you look at this first function, I don't know, maybe you're even inclined to distribute your 3 here. You can see that this is really y equals just 3x minus 12, which, if you think about this, is just a line that exists from left and right forever and ever. So if I even go express this graph here, y equals 3x minus 12, I think it'd be helpful to see the graph here. You can see that this is a graph just go left and right forever and ever and ever, just because it is itself a linear function. And so we would see that this would exist everywhere and everywhere. Now, in terms of its function, how can I tell you this? Well, here's the thing. Look at this. Are we ever going to have an expression that divides by 0? Well, no, we're not. And do we have any radicals that are hanging out anywhere? No, we don't. So in terms of the domain of this first function here, and this is important to me, it's important that we write it as the interval of x values for which our function is defined, which was negative infinity to infinity. Now, when you look at number 3 here, I already automatically, my eyes go right to this denominator right here, and I say, hey, you know, there's an x down there. And so what we're going to do is, because we're running the risk of dividing by 0, remember what you're going to do is you're just going to set your denominator equal to 0 and say, well, what would cause this to be true? Well, the only thing I can think of that would cause x minus 4 to be 0 is if x was equal to 4 right here. So in terms of the domain, I do want to show you this graph here, 3 over x minus 4. Not that you need to know what this looks like. You just need to, y equals 3 over x minus 4. You need to know kind of what it looks like here. We see that I'm going to graph a vertical line at x equals 4. There's like this x value right here that our graph never ever crosses. And so if I were to highlight the x-axis everywhere except for at negative 2, so we say the interval from negative infinity up to 2, excuse me, here, this is a 4, isn't it? Oh my goodness, you guys, this is a 4. Sorry. Is it a 2 back here? No, it was a 4. I totally am sitting here saying 2, and I mean 4. Basically, we see that our graph, our interval of domain values be negative infinity to 4, not including 4, and then starting on the other side of 4 and going to infinity. So the way we would say find the domain of something like this is, if you ever have an x expression in the denominator, set it equal to 0 and find what would cause that to be 0, because then our domain is just going to be all values except for there. So negative infinity to 4 in union with 4 to infinity, these would be the intervals at which our graph is existent. Number 5, okay, I don't see that I'm ever going to divide by 0 on this one. There are no x's in the denominator, and there are no even index radicals. So automatically I'm just going to tell you its domain is negative infinity to infinity, and even more because this is just the graph of a quadratic thing, a parabola. Now looking at number 7, I have 3 over this expression in x here, and so here's what I don't want to do. I don't ever want to have my denominator to be equal to 0. So what we're going to do is you set it equal to 0, and you say, what would cause this to be true? Now, because this is quadratic, I've got some choices. We can complete the square. Nobody ever chooses that one, by the way. We could factor it, which this does factor, or we could go graph it and look at the x-intercepts, or I suppose we could use a quadratic formula if you're just feeling bored. So it looks to me like I get x minus 5, x plus 3. So if I said, well, what would cause these to be 0? Well, remember, if this times this equals 0, then we're going to go set individually each of these factors equal to 0. X minus 5 equals 0, x plus 3 equals 0. The only way that the whole expression equals 0 is if either x is equal to a 5 or x is equal to a negative 3. So because we want to write this in interval notation, number 7 here, I'm going to try to squeeze this in. We would say, well, it's negative infinity up to the very first spot where we were undefined. And if we're going from left to right, we say negative infinity to negative 3. In union with, well, suppose from negative 3, but not including negative 3, we have a parenthesis, up to 5, And I suppose starting on the other side of 5 and going out to infinity, you can see that basically our domain excludes any values of x for which we're going to divide by 0. So speaking of, what would we have to put in for x down in these two expressions to divide by 0? Looks to me like -7 or +9. So if our undefined values here are -7, +9, let's write our domain. We say -infinity to -7, -7, let's write our union here, -7 to +9, in union with 9 to infinity. You would see that these are basically all the x values where we're going to exist. Now looking at number 11, we would have to set both of our denominators equal to 0 to say, well, what would cause this to be true? So in the first case, you would see that this is a sum of two squares. Actually, you cannot factor a sum of two squares. You could even try to subtract the 1 over, but what you're going to find out is when you take the square root of this negative right here, you get a plus or minus imaginary anyways. And so there's no real number that's ever going to cause this to be 0, so I don't see any reason why we would exclude x values there. But when you look at this x squared minus 1, well, suppose we solve that by factoring, we would get x plus 1, x minus 1, and if we set each of these individually equal to 0, you notice we get plus or minus 1. So our domain on this entire function, okay, I'm going to write in green here, would be -infinity to -1, in union with -1 up to 1, in union with 1 out to infinity, and you can see that the only values we're excluding here are -1 and +1. Cool. So if you ever have an expression that you're going to have an x in the denominator, set the denominator equal to 0 and solve for what would cause that to be true. Now, looking at these functions over here, you'll notice that this is kind of the second stipulation. Remember, we can't have negatives inside of an even index radical. These are all square roots here. So, because that's the case, if this is ever going to happen, what we do is we say that what's in here has to be either positive, greater than 0, or equal to 0, but not negative. So, that's what you do. You set all the interior stuff here greater than or equal to 0, and we say, well, let's go solve this. Well, a good thing is we have a lot of practice in solving inequalities like this. I suppose I like to write equations a lot. I wrote equals. X is greater than or equal to -2. I'm going to say that these are the values right here that would cause our x in here to remain either 0 or positive. Think about this. If you plug in -2, you get 0. Anything smaller than -2 would cause you to be negative. So also looking at the graph of this, we would say on the x-axis, at least the graph of our domain here, we would go right to, and we would say all x values to the right of our graph. So if you can imagine, this is really just a square root graph that's shifted right to. If I were to graph it in the xy coordinate plane, it looks like that. So we see that all you got to do is take the inner stuff, set it greater than or equal to 0. Unless, well, what's the unless? Well, unless the radical's in the denominator also. Because would you want this to be equal to 0? And I suppose the quick answer is no, you wouldn't want that. So this time, we're going to take our x plus 2, and instead of setting it greater than or equal to 0, because it's in the denominator, we just say we just want positive values. So if I subtract 2 from both sides, I get x is greater than -2. We would say that our domain here would be all x values greater than -2, but not equal to -2, because then you would get 0 down here. So you see the difference between these two is where that radical is located. So looking at these here, we do want to write the domain in interval notation. So because it's greater than or equal to -2 here, we're going to include -2 and say that it goes out to infinity forever and ever. And down here I would say its domain is actually just at starting on the other side of -2, but not equaling -2, because if you do, you'd get -2 plus 2 is 0, and the square root is 0 is 0, and 1 divided by 0 is undefined. So taking a look at this last one here, I would say, okay, so what's the domain? Let's take the quick route, okay? I'm never going to divide by 0 here, but I do notice that I have a radical that's an even index. So we're going to take what's on the inside of it, and because it's not in the denominator, I just say greater than or equal to 0, and we'll just go solve this. So I get 7x greater than or equal to 70. To divide both sides by 7, it's a positive 7. We don't have to flip our inequality, and so this would imply that we only want x values that are greater than or equal to 10, and therefore our domain would be starting at positive 10 and going greater than or equal to that thing. Cheers.